Welcome to all of you people. And okay, so welcome to all of you. And I'm going to give you, like, it's unfortunately I couldn't be with you people, but I will give a talk on matching and covering, very light, and give you some introduction to what you should expect in the workshop to learn and to see. Okay, so let me see if I can. Okay, okay. Let me see what I'm. Do you see my full slide, or you do you see just like slides in the slides? Okay. Now, is it the full slide now?
Yes, sir. Slide is visible.
Okay, thanks. So I'll talk a little bit about what is called matching, covering, structure, algorithms, and a little bit about the workshop. Okay, so let's get started. And okay, so some of the common terms that we tend to hear are like committees or panels or teams. And I was doing some I or task force, and if you look at some dictionary on the website, you will find some of the synonyms for committees are you know uh, like board, bureau, panel, representatives, trustee. So these are the very common terms that we listen all the time. And so a very natural question is that how someone form a team, or how does someone makes a committee. So this leads to this very common generic question of what we could broadly classify as committee selection, team formation, and things of this nature. Okay. Okay, so what is basically selecting a committee means? So selecting a committee means that we are selecting a group of people of size k that satisfy certain constraints. Okay, such as you need some experts for the roles of the committee. So you're not going to select a committee for anything, right? It is supposed to do some purpose. So you need to find set of experts who will do that job for you. Okay, or you also need some sort of diversity, that you want to meet that people of all kind, like gender balanced or race balanced, or everything is met. So there are different constraints that is put on the committee, and we need to form a team or group of people who satisfy these set of constraints. Okay, does anybody recognizes this term, 4 plus 2 plus 4, or maybe this, or maybe this? Has anybody seen this?
Sir, these are football formations.
That's right. So they are football formation. Correct. So they are basically this is basically a team formation in football, and like generally coach, or like the whatever coach, or generally coach, or manager sets up the team in a way that it can act in an organized way. Okay, so this is like a team formation in football. So so what so like these the four at the end are basically called defenders or back. then there are some midfielder, and then there are some people who are in the front, like striker or forward. So a team, you just think of this way, right? I cannot fill my team with some 10 defenders, or I cannot fill my team with 10 forward player, 10 striker. I mean, sometimes we do. But maybe some of these players could play a role for both a midfielder as well as forward, or a midfielder or back, some things of this nature, right? So in general, this, like, all I want to tell you from this picture is that team formation is omnipresent, and especially now that people are watching football matches all the day, I mean, this is very natural. So which basically leads to the form. For example, here are some people, and imagine that a circle represents to you that, these are the set of people who could perform a task, or they are specialized in, for example, these are the set of people who are forward, for example. Okay. And these are the set of people who are midfielder, who could act as a, both as a forward as well as midfielder. So, and these are the people who could act like forward, midfielder, as well as, like back. And this is a role of a goalie, which only consists of, say, one player, maybe two player, and so on and so forth. So so there are a set of people or set of objects, and objects are classified or tasked with a role of, a role with like what is the what particular task they can perform, or what particular role they could play. So this is a very simple example of team formation, or a consisting of a committee. And for example, if it would have been some ethics committee, so then we need some gender, I need certain ethics from computer science, ethics from math. So different set of people or different field will have different ethics, and a committee or the group could act just differently. So this is a very typical formation. So if you just abstract the problem, then what is happening? Constraints correspond to the group satisfying the constraint, of course, and committee correspond to finding a group of K person that is a representative from each group. So this is like most simple thing, that you want to have a representative from each of this group. And so basically our objective is to find K people that covers, heads, intersects all the group. And this is what is prototypical covering problems are. So you have some set of constraints, and you want to find small set of objects that covers all the constraints, that hits all the groups, that intersects all the groups. Okay. So in this example, if I take just this, it does a role for whatever it does, right? So these two persons can intersect all the constraint. So that's one very basic type. But this may not be the everything that we would be interested in. Maybe we need X number of forward, or Y number of midfielder, or Z number of reserve. So you might also could change your question that, hey, you could give a function which can tell you that from each group, how many members you need, right? So you can start with a very simple, typical problem, and based on your need, or based on your constraint, or based on your requirement, you can just modify this covering problem a little bit. Okay. So this is what it is. Like, you have universe U, family F of subsets of the universe, integer K, and you are asking, does there is a K size subset H of U that intersects every set in F? So this is why it is called covering problem. So if we forget team formation, then what is happening? We have a universe U, like for example, team of people. And what is family F of subsets? These are the set of people there which are classified or grouped together with the task that they can perform together. And integer K, and you're wanting to find a representative that hits every set in F. Okay, so this is what happened in the example. But as I was talking about, this looks too much. Like, this doesn't seem like some sort of fair committee, in the sense that why it is not seems like a fair committee, because it's like the one person here is like he's able to perform tasks for everything. But you do not want just one person. Maybe you want a committee where there's a representative from every group could say, hey, here is my private representative, here's my private unique representative, and things of this nature. So committee that we formed was representative. It was able to intersect everything. But one person was taking care of three groups, which we didn't like. So new constraint, let's try to put that every group must have a private person that takes care of the group. So you want your private person to whom you can go and complain. Okay. Or who takes care of your needs, right? So in that sense, we want certain fairness constraint, or you can put anything else. Now let's try to see what this happens. So now we are finding a covering so that each group can be matched to its unique representative. Okay. Now, does this remind you of a problem that you might have seen? Right? So now we are not only interested. So I want that you hit all these people, but I also want the fact that every group has its unique representative. Okay. So how can we formulate this question properly? So as follows. So each constraint corresponds to a group that satisfies the constraint. Now we can make a graph with one side having a vertex for each group and the other side having a vertex for each person. And if a person belongs to a group, then we add an edge between the group vertex and the person. So for example, for this example, or maybe like just typically, so this is what will happen. So you have a group vertices and you have a people. And if a vertex appears in their group, so I put an edge. Now, what are we looking for this? Then we are actually looking for this. So for every group, I want to find a representative which is private to this. So what is this? This is, anybody? Isn't this matching? Right? This is nothing but what we just now saw. This is just matching. So because everybody needs a private person, which basically means that for this group and this person, like this group person pair is not matched by anybody else, which basically means that you are looking for a set of edges in this graph that do not share any endpoints. So that will lead to a, so we first saw a covering problem, and then this is our new problem, a matching problem, which is where you're given a graph G and you will find a matching of maximum size. And this is called maximum matching problem. Or you could put weights on the edges of the graph and you want to find a matching of a maximum weight. So that will correspond to maximum weight matching, right? So if you look at some of these applications, like either you have some prototypical covering problem or prototypical some matching problem. But if I look at this example, maybe you may not just want one person, but you want, hey, like I need two private people. So basically you're not looking, so that will lead to a notion of one-to-many matching, right? Or, right, because one team or one group might need 2-3 people, or the second group, and all these are unique. So then based on that, like what kind of matching you're looking for changes, and the question that you would like to solve also change. But they're like some sort of generalization of matching. So these are some simple basic prototypical problem, and based on your need, people study different kind of questions. Okay, so you will see. So another viewpoint that we can take on matching is like you're packing edges, right? So what is packing? Packing basically means that you're trying to find set of objects that they are paired by a disjoint, okay? And you want to pack as many objects as possible. So now imagine that you're trying to pack edges in your graph. And what is the property that you expect from this edges? That you want to find set of edges that do not share any common endpoint. So this is like packing. So matching we can also think of as a packing edges. So this is what. So you will have some set of talks which will explore relation between how covering and matching are related to each other, okay? So you will learn about structure and algorithms for matching in bipartite graphs, and covering and matching in bipartite graphs, like how this edges and covered problem are related to each other in bipartite graphs. You will have some set of talks on that, and you will also learn about an algorithms for matching in general graphs, but it's a bit more complex. So we decided to do randomized algorithms for the problem, and you will have a talk about this using Tut decomposition or Tut matrix. And the reason was that like all these covering problems also has a very interesting relation to algebraic algorithms or randomized algorithms. And this talk or lecture will explore that aspect of this. Okay. Now we come with the next notion, graph with preferences. Like for example, think of these groups. So think of that left-hand side is colleges and right-hand side are students, and students would like to go to these colleges, right? But then they will have preference. Like, for example, maybe some students, when they're applying to US, they would be interested in, okay, first I would like to go to MIT, then second preference will be Princeton, okay, maybe third preference will be Rutgers, or fourth preference will be something. So every student has a preference on the colleges, right? Similarly, right? So imagine that this is like a one-sided preference people have, right? So now you still want to match students to the colleges, right? But like, is every matching similar to what they want? But like, because now we have a ranking, so every student ranks this. So, but maybe you start with some matching where student is matched to some colleges with certain, but maybe there is some different matching that might be able to satisfy the students much more. Now, what is the meaning of that satisfaction is, right? Right? So this leads to this, this notion of what is called stable matching. And stability is just one core concept, but stability is defined with respect to the requirement, with respect to the need, in that, okay, this matching is good, but like when we do not have preferences, it is matching about just one side, okay? But now when you start putting, when there is no preference both sides, just a normal matching, but when you start putting preferences, it is not, apparently it's not clear that first of all why such matching should exist, and even if it exists, why is particular matching better than the previous matching, or what is a notion of good matching, okay? So we will explore these aspects of matching. Now, why in this example there could just be preference from or ranking from students? There could also be ranking from the other side. For example, like the way many of these things are set up is like marriages, or a college could also have preference over students. So like preference could be from both sides, from the college side, student side, partner side, every side. And then you still need a notion of matching, because that's all that you're doing, and how it is to be done, what definition to be chosen. Oh, this matching is good because it has certain features. So you will learn about some of these things when we will do fair amount of matching with preferences. And then what is fair allocation? So you can think of matching as like you are allocating colleges to student, right? Or you are what do you call? So, but maybe there is much more wider notion of allocation. Could be like, imagine that you're working in a government or something, and you want to allocate some money to poor people, or you want to allocate money for education, development, and everything. So there's just one pot of money or something, and you want to allocate an items for different activities. Or there are people who needs different set of things, and you want to allocate little bit of everything to everybody. So like we can go general from matching, and that will lead to notion of allocation, and what is the notion of fair allocation and everything. So there are some 4 or 5 lectures which takes this one matching to like multiple objects to multiple people kind of situation scenario, and how to do stability, how to do fairness, that nobody is unhappy about it, everybody's like. So that aspect of matching and allocation will be dealt in this workshop with some 3-4 lectures. So just wait for them. Okay, now let's go back and let's revisit committee selection. How does committee are selected in democracy? How do you make a parliament in a committee? Or like parliament is sort of committee, like some sort of representative. That how do we do that? Anybody? Do you understand my question? So if I wanted to form committee in democracy, how do we generally do these things? Any idea?
Sir, elections.
Correct. So elections or voting. Okay. So what is voting? Basically, you have list of candidates. People vote by giving ranking over candidates, and you have to select candidates. But I mean, I said lots of things. People vote by giving a ranking over candidates. What ranking are we talking about, right? Right, in the sense that can they be, do you have, are these strict ranking, like I prefer 5 over this, like candidate 5 over candidate 4, or like I could be ties also. So we have to think about now which rule for selection, right? I mean, how do I decide 5 people, or even how do I decide a winner, right? Because is the winner one who got the most number of first choice vote? Okay, but maybe there are two people whose first choice votes are same. Then should I go to the second choice vote? How many people prefer them as second? And so on and so forth. This leads to different notions of selecting a committee, selecting a winner. So you will learn some lot things about this in some 3-4 of talks about when you learn voting and like liquid democracy and some of these kind of things that you will learn these concepts and different set of rules that people have used in practice as well as in theory to select a committee, select a group of people with certain preferences. Okay, so we will have some set of talks about these also in this school. Okay, so we talked about these covering problems like universe U, family F of subsets of the universe, interior K, and basically you're looking for K size subset H of U that intersect every set in F. Now let's look at this specialized covering problem, right? Where now I'm not talking about any arbitrary family of subsets, but family of subsets of size 2 of the universe, right? That looks like a very simplest case. If it is size 1, you will think that it's like something very simple and trivial. And this is basically vertex cover. So if you specialize your abstract covering problem, where a family consists of size 2 of the universe, then this leads to what is known as a vertex cover problem in graphs. Okay, and how do you think of this as a graph? Basically, you think of universe as a vertex set, and for each family in your family of subset, it's a two-side set. So you look at those two elements and you put an edge between them. So this is how you can go from a covering problem where size of every object that we need to cover is 2 to a graph problem. Okay, but you will learn following things. So vertex cover is NP hard. So no known polynomial time algorithms are known. So we will tell you a little about this and how the notion of interactability has evolved over the last 3 decades and 4 decades, and we will choose some of those important aspects of those developments in interactability. And there are a couple of interactability lectures that you will have where you will see how to show something is hard, meaning, and what I mean by hard, like there are no polynomial time algorithm. So many of the things which we just talked about before about covering and matching of some of those things, some of those can also be done in polytime, but some of those also have lots of NP hard variant, and we will spend a significant amount of time discussing those things and like evolving some of those things. So look out for these interactability talks in the workshop, which will fill this gap when I can show something is polytime or when I can show something is hard in what regime. Okay. So now that we have shown that there are some problems, some very beautiful problems are polynomial time solvable, some beautiful problems are NP hard problem, then what to do? So basically what NP hardness will mean that there is no algorithm that can solve all instances optimally in polynomial time. That's all that it means. Like in a practical aspect, when you say a problem is NP hard, all that means that I cannot design a single algorithm that can solve all instances optimally in polynomial time. Okay. So coping with NP hardness. So how do you cope with NP hardness? Okay, so notice that a lot of time we see that some problems are easy on trees, or yeah. So what is the meaning that they are easy? So like on general, the problem is hard. For example, look at this vertex cover problem. If you restrict your inputs to trees, the problem is easy. Or when I say easy, it can be solved in polynomial time. So this leads to restricting input on, or this also leads to this notion of parameterized algorithm, which we'll talk a little bit about this. Or what you can do is that you can forego, optimality. So like, okay, I'm happy, for example, for a covering problem that, it's okay if you don't give me K size objects that can cover, but even 10K size object is fine. So we forego optimality and we say a slight approximation is okay. Okay. So if we restrict ourselves to polynomial time, but we forego optimality, and that leads to the world of approximation algorithms. and or we can forego polynomial time, right? So we still want something to be done in exactly, but we can't solve the problem in poly time because this is NP hard or something. Then we forego that and we allow exponential time to be taken to solve this problem. So there are different mechanisms to cope with this hardness. Either you restrict input, or you forego optimality, or you don't care about polynomial time, but you still want to design a good algorithm, but you're allowed to take non-polynomial time or super polynomial time. Okay. And there's also a notion of kernelization that we'll see in a minute. So approximation algorithms for vertex cover. So what's an approximation? So the best heuristics to apply is like a pick a vertex of highest degree. Or there's another heuristic which is very nice, which is greedily packed obstruction. So what are an obstructions to a vertex cover? If you notice that basically what is vertex, you have to pack the obstruction. So your obstructions are this covering object. So what I mean by covering object, these edges, right? So you think about this following algorithm. You greedily pick an obstruction. You know that any hitting or covering object must hit this object. So you pick up both of these elements greedily and put into your solution. So you can greedily pack the obstruction. What kind of approximation it will lead? What kind of approximation the first heuristic will lead? We'll discover some of these things in the approximation algorithm. And sometimes you need matching for this. So if you're trying to greedily pack the obstruction, it is good to take maximal such matching, but as small as possible. So is that what is the running time of those algorithms? So we will see some of these things when we will do with approximation in the course. Okay. And so kind of question that we'll try to address with some examples are, does all problems have good approximation? And how can we show some problem is hard to approximate? Not only that we can't design a polytime algorithm, it is even hard to get approximation in polytime. So there's a whole well-oiled machinery to show some of these things. We'll try to throw some light to some of these aspects of approximation algorithm in our course. Okay. Don't get confused, guys, okay? Size matters. So how much does the size matter? The bit size of the input instance is never the only thing that affects the running time of an algorithm. For example, BFS, DFS is linear time. Subset sum is order NT, right? We know that subset sum is NP hard, but it has an algorithm with running time order N into T. So if imagine that the target object is like a polynomial, right? And why it is NT? Because what is target? For the target, the amount of bits that you need is like log T bits, right? So if the subset sum would have been polynomial time, we needed to design an algorithm with running time N log T to the power bigger of 1. So if you, in the input side, subset sum algorithm is actually an exponential algorithm, where T is like, in terms of number of bits, is like 2 to the power number of required bits of the target, right? So it is an FPT algorithm in that sense, but we'll see what I mean by this in a minute, okay? So I mean, people can use different aspects of the input to design good algorithm, right? For example, K-SAT. So there is more. Yes, there are number of clauses, number of variables, but we also know something more, that the clause size is bounded by K. Can be exploited? Yes, we can. If we can exploit it, then you get this kind of algorithms, which dependency also takes care of the input, how it looks, how it in its running time. Okay. Or for example, that K-click, you want to find set of K people or K vertices that they mutually know each other, or they mutually have an edge. So these things will take running time n to the power K plus 2. How? You just try all K possible objects and check whether they form the desired connectivity or not. Okay. So what is parameterized complexity? It's like measuring the running time of algorithm as a function of size and something else. Okay. And largely be applied to NP hard problems, but it can also be applied in different settings like approximation algorithm, polynomial time algorithms. And so let's look at example for vertex cover. So your graph G, integer K, and our question is there a vertex at S such that every edge has at least one endpoint in S? So here is a 2 power n square algorithm. You try all possible subsets like n choose K, or you can evaluate the running time by n to the power K plus 2. So this algorithm is polynomial for every fixed K, right? So if you're looking for a 3-size vertex cover, then this algorithm runs in n to the power 5 time. If you're looking for 25-size vertex cover, then this algorithm runs in 27. And these are what is called as slice-wise polynomial or XP algorithms. Okay, and in the world of parameterized complexity, we try to design an algorithm with running time f of k n to the power g of k. And yeah, so this is basically what XP would mean in the current setting. Okay, but like we saw 2 algorithms for vertex cover. Let's see slightly different algorithm for vertex cover. Okay, so this was given by Bus maybe before 1993. So here's a very beautiful algorithm by him which says pick up a vertex of degree k or more in the solution. Why? Because look, if you have a vertex of degree k or more and you are trying to find a vertex cover of size k, if you don't pick this vertex, then you have to take all its neighbors, and then you already have incurred, like, budget is much, much higher. Okay, so you delete and decrease k by 1, and vertices of degree 0 are relevant because they do not cover any edges, so you can delete them, right? So now either by this process, you'd have realized that it's yes or no, or you're not able to apply these rules, and what you're able to come up with a conclusion that every vertex is degree at most k. Now, if you have k vertices, now imagine that like one vertex can cover k edges. So k vertex into total can only cover k square edges. So if you have more than k square edges, then you know that you cannot find any k vertex that can cover these edges. So you can very clearly say it's a no instance. Okay. And if it is less than k square edges, then it has less than 2k square vertices. And now you are grieved because you can do brute force, and that will be k to the power big O of k algorithm, right? So now this n choose k plus n to the power k plus 2 algorithm, if you replace n by k square, that is k to the power big O of k algorithm. So you could be slightly more smarter. And this is the kind of parameterized algorithms that I have been talking about. Okay, even better. Okay, so you know that if you have an edge, then at least one of u and v must be in solution, which imply that G has a vertex cover of size at most k, if and only if either G minus u has a vertex cover of size k minus 1, because you know that one of u or v must be in the solution. So you delete this and you are looking for a vertex cover of size k minus 1, or G minus v has a vertex cover of size at most k minus 1. At least one of these two statements is true, right? So if we are looking for a vertex cover of size at most k, then either G minus u has a vertex cover of size at most k, or G minus v has a vertex cover of size at most k minus 1. Now you can recurse, and that's it. So what's the running time of this algorithm? So when you had a unit, k unit, you ask 2 questions with k minus 1 units. And when you have a question of k minus 1 unit, you ask 2 questions of k minus 2 units. So the depth of this tree is bounded by k. And so the total running time of this algorithm is number of nodes in this search tree, which is like roughly 2 power k plus 1, which is like 2 power k into 2, and polynomial amount of time that you spend on each node. So this is 2 power k poly n algorithm for vertex cover, right? And this was given by Mike Fellows and Rod Downey. So you could combine both methods also. Like, for example, in polynomial time, k prime is less than or equal to k, number of edges is at most 2k squared, and on that you apply this 2 power k nc algorithm, and you get this. So you can combine these 2 methods also. So same problem, we saw 3 algorithms, n to the power k plus 2, this, same polynomial for every fixed k, and this is what is known as fixed parameter tractable algorithm. Like, it is same polynomial for every fixed k. It is not like the dependency on the input size depends as k grows, the dependency on n with respect to this k grows. No, it's just a constant which changes, but the dependence on the input size remains same. And this is what is basically fixed parameter tractable, on which we will spend some 5-6 lectures. Okay. So basically, we try to design an algorithm with running time f of k n to the power c, where we decide a priori that what is an aspect of input that I'm allowed to be exponential n. Okay. So our all problems FPT is finding a maximum matching of size, maximal matching of size at most k is FPT, right? So we talked about that finding a maximum matching is easy. But if I said I'm not interested in finding maximum matching, because for covering it is important that I pack as few constraint as possible without and still being maximal. So I want to find among all maximal solutions the maximal solution of a smallest size. For example, is maximal matching, so of size at most k. Is it first of all NP hard or poly time, or is it FPT? So these are the kind of questions that we will explore in the course. Are all problems in XP, for example, and so on and so forth. So we could also combine approximation and FPT. So this is where we'll get this very beautiful structural object called tree width. And we will see some algorithm to design some of this tree width. And okay, so sometimes we can use approximation and FPT, combine them, and get some beautiful algorithms. Like, for example, we'll look how if we look at covering constraints or covering objects, the covering problem, the prototype problem that we spoke about, and we say, look, it's okay that you don't, I give you some budget, it's okay that you don't cover all the constraints, but try, given this budget, try to cover as many constraints as possible. So if you want to cover not all objects or all constraints, but you want to cover partially as much as possible, then we can show that the problem is hard in the both approximation sense and both FPT sense. But if we combine both of these two worlds, then we are able to make progress or design some new good algorithm. Okay. Okay, so there will be a lecture on that. And then finally, why only time? Let's save some space too. And that leads to some small space algorithms that we will discuss a little bit. And we will also talk about this new notion of streaming algorithms, where things are streamed. So you can't keep everything that being streamed in the memory, but you only can keep small snapshot of this, and how to be able to reconstruct everything later by just looking at this snapshot or sketch is, we will spend a lecture on that. So that's all. So that like everything is tied together with respect to covering, matching. We explored all different possibility of matching, bring in some voting, bring in some democracy, and all these kind of things. And in one parallel, this thing, we take up this covering problems as a purely theoretical problem, and see what all methods or techniques we can evolve and develop on those. So there are two aspects of the workshop. One is this matching aspect, which leads to fair allocation, stability, preference, and there's another aspect which is dual to covering is packing. Dual to packing is covering, and that will lead us to the world of different algorithmic paradigm and things of this nature. And we will have talks on those. So it's like roughly it is divided in 50-50 on these two topics in the course. Okay, so with that, let me thank you and let me welcome you to the workshop. And hopefully we'll have an enriching session. And all the workshop will do is pick up the topics that I just described and give you in details what these objects are, or explore these objects or topics in full details. Okay, so that's a plan for the workshop. So until you have any question, I'm done for my talk. Thank you. Any question? Anything you like to ask?
So thank you, sir. I think there are no questions.
Okay, that's great. So okay, see you guys on Wednesday then. Okay, have fun till then. Bye bye.
Hello, hello.